All right, welcome back, everybody. Today we're going to be doing section 16.4, and we finally get to learn about Green's theorem. So this is pretty cool. Let me pull up the slides, and we will get started. Right. So this lecture will probably be a little bit long, kind of like the last one. Frankly, just whenever you're talking about all of these really deep results, you have to spend a significant amount of time on them. So I apologize if it's a bit long. But here is the overview. We're going to talk about what Green's theorem is, and then I'm going to deviate from the book a little bit in that I'm going to introduce curl in this section. The book actually saves the concept of curl for the next section, 16.5, which we will get to. But in order to talk about Green's theorem, I've just found that it's easier to make sense of it when you talk about curl first. But this kind of happens throughout the chapter because Green's theorem is really a special case of Stokes' theorem, which is really a special case of the divergence theorem. And these are basically generalizations of the fundamental theorem of calculus. So a lot of this stuff is kind of like the same, but more general or less general. That's basically what happens over the next several sections. Or at least 16.4, 5, and then 8 and 9. So that's why things are kind of like fluctuating. Anyway, so we'll talk about curl in this section, and then we'll revisit it in the next section. Then we're going to prove Green's theorem, and then we're going to get a very cute corollary and another cute result of that corollary, which is the tool known as a planimeter. There are lots of videos and stuff, so we'll see that in just a minute. Then we're going to extend the scope of Green's theorem to work on other types of regions. And then we're actually going to prove that theorem from section 16.3 that we weren't able to prove in the previous section. Although, let me see here. Let me do this for a minute. Oop. Hold on. Hold on a sec. There we go. Sorry about that. Just wanted to get something set up before I go to it later. All right. So here's the cool stuff. So Green's theorem actually gives us a very cool result about the relationship between the line integral of a simple closed curve and the double integral over the plane region D that has C as a boundary. So there's a relationship between integrating over the region inside of a closed curve and integrating over the line that is the boundary of that region. That's what Green's theorem gives us. And like I mentioned here, this is actually a special case of Stokes' theorem, which we'll see later in 16.8, and the divergence theorem, which is 16.9. And a lot of these well, frankly, they are the fundamental theorem of calculus. But you'll see this repeated idea of, hey, if you want to get an idea of how an integral is over a region, look at the endpoints or look at the boundary of that region and compute a value at the boundary. So it's the same kind of idea repeated multiple times. And I'll point it out again later here. So before we can talk about Green's theorem, we need one definition. We need to talk about what a positively oriented curve is. So this is the easy way to explain it. A simple closed curve, remember simple means it doesn't cross itself. Closed means it is closed. We say that that curve is positively oriented if it's traversed counterclockwise, as is tradition. And what that means is that the region will always lie on the left side of the curve. Wait, I guess for you guys, this would be the left side. So this is an example of a positively oriented curve. Notice the arrows are pointing this way. So as you walk around the region will always lie on the left side. We'll see this kind of thing again in a later section when we talk about orientable surfaces and non-orientable surfaces. But when you have this positive orientation, the region is always on the left side. If you were to imagine yourself like walking along this curve, the region would be on your left-hand side. This is a negatively oriented curve, so everything's literally the opposite. You're walking along it in a clockwise direction. And here you'll notice that the region is actually on the right. So that's the negative orientation. Okay, so here is the statement of Green's theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region with C as a boundary. If P and Q have continuous partial derivatives on an open region that contains D, then this integral here, the line integral over C, is equal to this double integral over D of this expression right here, this value right here. So That's what we're going to look at. Maybe this value looks a little bit familiar. Hopefully it does, because we're about to see why it's familiar. So here's one little bit of notation. So you will see this notation later on. Since C is the boundary of D, the conventional notation to denote the boundary is actually with this partial symbol. So it may feel like a bit of an abuse of notation, but it's not. Uh, so we can restate Green's theorem like so. If you want to do the integral of over the region D of this, then you could instead do the line integral over the boundary of D of this right here, that vector field. So the partial symbol just means that you're on the boundary. So this often means boundary. It's not an arbitrary choice. It's actually directly related to the fact that, for example, the surface area of a bounded smooth region is the derivative of the volume. So I know if you took me for Calc 2, and I think I mentioned it, did I mention it in Calc 1? Maybe oh yeah, I think I do in Calc 1 actually. If you take the derivative of the volume of a bounded and smooth region, you're going to get the surface area, which makes sense because the surface area is kind of like how much things are changing to get you the volume. Here's a really, really good example. This is a classic example. This is the one that I do in my classes. Remember the volume of a ball of radius r is 4/3 pi r cubed? Well, if you differentiate this function with respect to r, you get 4 pi r squared. And that happens to be the surface area of the sphere of radius r, right? This is the surface area of a sphere of radius r. So here, very literally, the derivative of the volume is the surface area. And the surface is the boundary of the region, right? The surface is the boundary of the region. So that's why you have this connection between a region and its boundary, and we use this partial notation just to kind of suggest there's a connection with derivatives, because there is. All right, so it makes more sense to talk about Green's theorem when we have a notion of this concept called curl. So we're going to talk about curl now. Yeah, basically what I said here. So we will explore curl again in the next section, but for now we're going to get the definition, and we're going to build some intuition for why it is the way it is, why the formula has the structure it does, and we're going to see some really cool animations from the website Math Insight, which is linked in the slides as well. So here's the definition. So let F be a vector field on R3, P, Q, R, and suppose that the partial derivatives of P, Q, and R all exist, then we define the curl of F, the curl of that vector field, to be a vector field itself defined by this equation. So this is the curl of F. And the first thing I want to point out is that the curl is a vector. Do I say that on the next slide? I think I do, yeah. Here it is. So the first thing I want you to notice is that the curl of a vector field is a vector itself. It's a vector in V3. We are going to restrict our attention to R3 or V3 and R2 or V2, mainly because, like the cross product, curl is only defined for vectors in V3, just like the cross product back in chapter 12, right? You can generalize this idea to higher dimensions, but then you need a more general theory of calculus, which many of you won't see. You have to learn about exterior algebras, which I mentioned before, and I dropped a Wikipedia link at some point in one of my earlier lectures. But for now, we are just going to assume that curl is only defined for three-dimensional vector fields. And you can get two-dimensional vector fields by just setting the third component equal to 0. So there you go. So what is the curl of a vector field? Well, you can visualize it by imagining a ball spinning or not spinning in place under the forces of the field. So as an example, imagine you had a ball like submerged in a hot tub, and the jets and the water in that hot tub are flowing around, right? Well, imagine if you could submerge a ball in there. How would the ball spin if it was just held in place? Would it spin at all? Would it spin clockwise, counterclockwise? Which way would it be? Which way would the axis of rotation be? Would it be like, would it be up? Would it be to the side? That's what we're talking about. So curl is basically giving you that vector, which is the axis of rotation, and then how fast the ball is spinning and so on. Okay. Yeah, so the axis of rotation of the ball is the direction of the curl vector, and the magnitude is the speed at which the ball is spinning. And a very good way of thinking about it is that curl is essentially the microscopic circulation at a point. So when you talk about curl, you're really looking at how much the vector field is making something spin if you were to like fix a point of interest, like look at a single point, and how is the vector field going to spin things at a point. So there's a good website that has a lot of animations on it. We're going to look at a few of them right now. It's called Math Insight. I encourage you to follow this link and mess with these animations on your own and just read what they have written there. I'm going to go through some of it, but I won't go through all of it. Another suggestion I have is that you check out Grant Sanderson's video on curl. His channel, maybe you've heard of it at this point, is 3 Blue, 1 Brown. Frankly, any videos that he's got, pretty much any of them, I would recommend. So I would recommend it. Not only that, his video on curl and divergence is a required supplementary video in the next lecture. So when I do the lecture for 16.5, there will be a point where I'm like, all right, pause this video and go watch his video because the animations he has in those videos are just perfect. They are perfect. They give you so much intuition about what divergence is and what curl is that you just have to see it so that way you can move forward with the sense making process that we're going through here. Okay, okay, let me do this first. Notice that with this curl vector, what's happening is that each component function, these guys right here, they're giving you the kind of the amount of curl in a certain basis direction, I, J, K, right? And we're going to focus on the last one, but before I do that, yeah, this is a good time to look at these animations. So let me pull these up and we'll take a look at them right now. Okay. Hang on one second. Where'd you go? Right there. Oh, change the size. Give me one moment here. There we go. Okay, let's take a look at these. So this is where you'll be taking if you follow the link. I'm sorry, my video might start to not rasterize, but jitter a little bit because using a lot of memory on my computer here. So this is basically the idea of a curl, the curl of a vector field. You can imagine a vector field here, right? Oh man, I don't know if my computer can handle all of this stuff, but here's the spinning ball example that I was giving before, right? So on this website, you can like rotate things. You can see how these things work. Yeah, it's going to be more jittery than I was hoping. You can kind of see it there. Okay, there we go. So there's this potential relationship between macroscopic circulation and microscopic circulation. So the ball is basically where we fix our focus and we look at the microscopic circulation at that point. So here's the ball. And what you can do is you can like move the ball around through the vector field and see how that microscopic circulation affects the spin of the ball, right? So there's forces in the force field that are causing the ball to spin in this case, and it's spin in place. So when you fix it and you don't move it, it's still spinning right there. All right, oops, scroll down here. There we go. However, there is one caveat here. Curl is not so simple as like, oh, if I see a rotation or if I see a macroscopic circulation, then I must have microscopic circulation. So there's this whole bit down here, scroll down, about not getting misled. So just because there is a big circulation going on in a vector field, it does not mean you're going to get microscopic circulation, not necessarily. So you need other conditions to guarantee that kind of stuff. So if you follow this link they have here for subtleties about the curl, it will lead you to another, do I have it right here? Subtleties about the curl. Yeah. Okay, so here's an example. And they've got the vector field negative y, x, 0. So this is the vector field here. And you can kind of see how the ball is like spinning around. And here the ball is rotating around. So this is a circling, sorry, there we go, circling sphere in a rotating vector field. So the sphere is circulating around the z-axis due to the macroscopic circulation of the fluid flow. But the macroscopic circulation is not a measure of the curl. So you got to be careful. Curl is a point-wise defined object, mathematical object. So that's why they mention here in this next paragraph, if you want to measure the microscopic circulation, you have to fix the center of the sphere and allow it to rotate freely. So check this out. And these applets are pretty cool. You can move these objects around. Although mine's pretty jittery. Sorry about that. There we go. So you can investigate these on your own and just kind of play around with them. Um, maybe better than I can do live right now. So here's a sphere, and notice that when it's fixed, it's spinning. So there's a curl going on there. Curl is actually non-zero at that point. However, you can have a macroscopic circulation that doesn't admit any curl. It doesn't admit any microscopic circulation. So this is an example here, and I think he actually has the, where is it? Oh, I forget what it is. Is this the, where is it? Thought he had, oh yeah, he has the vector field given right here. This is the vector field. So let me scroll back up for a minute. In this example, you can see that there is a macroscopic circulation, like objects are getting moved around. But if you look at the ball itself is not spinning. And that's emphasized in this applet right down here. And this is where you can move it. So if you move the ball around, the ball itself is not spinning. So there is no curl. There's no curl, right? And this is actually the vector field here. This is in the example that I use in one of these slides as well. Okay, there's some other cool things. You can have curl that is the opposite of the macroscopic circulation. So there's all these possibilities here. Here's a vector field where the curl is actually spinning in the opposite direction of the macroscopic circulation. And this one's kind of fun. So check this out. As I move the ball away, you can see it spins slower, but then as I move the ball closer, it starts spinning, oop, very, very quickly. So you can even have situations where the curl is in the opposite direction of the circulation in that sense. There you go. And is there a relationship? We're about to see the relationship. So this is where those conditions that Green's theorem has in order to make it work. The conditions that the region be simple is important, because if the region is not simple, then you can have issues. You won't get that connection. And there's also this bit here where the circulation may not be obvious from the pictures. So again, a picture is not a proof. Like I mentioned in my classes, you can use pictures to give you some intuition, but they're not enough to base mathematical fact on. You have to actually prove something mathematically to say that. But here's an example where if you look, uh, this is just a straight lines, right? But it's causing this microscopic circulation. It's causing curl. And look, you can even see the arrow that indicates the direction of the curl there. That, I think, oops, no, there it is, right there. And then is this the one? No, that's the end. Oh yeah, this is the one. So if I move this, watch the green arrow. Watch the green arrow here. So as I move away, the length of that vector gets smaller, because curl is a vector and the curl is shrinking in size as I move away. But then as I move closer to the origin, the arrow grows in size because the curl is growing very rapid in magnitude, or very large in magnitude. The curl is, the spin is getting faster and faster. There you go. Okay, so strongly encourage you to look at this website, mess around with these applets on your own, look at the pictures, make sense of them. They're really, really helpful. But let's get back to the slides and look more at the structure of the curl formula. Here we go. Okay. There we go. And be sure I got everything. All right. So where was I? Oh, yeah. So look back at this formula for a minute here. And what each one of these component functions are doing is they're giving you kind of like the amount of curl in a certain basis direction. We're going to focus on the last one for now. Hopefully that's the one that looks familiar from the previous lecture, right? So one thing to note here is that this component function, it's in terms of the functions p and q, because those are going to correspond to the behavior in the I and j directions. If you remember f, right, f was pi plus qj plus rk, right? So p and q are kind of corresponding to the I and j directions. That's what's going on. And basically what happens is if that behavior doesn't cancel out, if the behavior of P and Q in this sense, and if the change in their behavior with respect to X and Y in this way, if those don't cancel each other out, if this term is not, or sorry, if this coefficient is not equal to 0, then there's going to be some degree of curl in the Z direction, or maybe I should say in the K direction. So just to restate, if this is not 0, then you're going to have some amount of curl in the k direction, or the z direction. So now let's look at this expression here and see why it's structured the way it is. Why does it actually look like this minus this? Let's get some deep intuition for it. So what we're going to do is this. We're going to take a bird's eye view of our ball. So imagine you've got a ball submerged in your force field. This is that last term that we're looking at. And we're going to project our ball down onto the xy plane, just like this. So now we're going to look at the influence just in these two dimensions, right? The green disk is basically our ball. Oops, excuse me. Oop. Oh, there we go. Okay. Now, so think about it like this. If we wanted this disk to turn counterclockwise, then we could have the j component of f, that's q, we could have it push upward on the disk, right? But if we wanted the rotation to be counterclockwise, then we would need q to be stronger on this side and weaker on this side, right? So try to imagine this very, very intuitively. If I wanted the ball to spin this way, I could basically push on this side, right? But I could push on both sides, but I need the push on this side to be much smaller than the push on this side. And if the push on this side is larger, it'll make the ball rotate, right? So how do we encode that mathematically? How do we write that in terms of mathematics? Well, what we need is we need partial q partial x to be positive, right? So remember, q is like the j influence, right? The j influence. And basically, as x goes from left to right, we need the change in q, the speed of q, to increase. We need it to increase. So as q goes like so, I'm sorry, as x goes like so, we need the change of q with respect to x to increase. That's what this means. So if the change of q with respect to x is increasing, we'll get this counterclockwise rotation. Right, but that's not the only thing we can do. We could also achieve this counterclockwise rotation if the I component of the force, P, pushed the disk to the right. Oops, sorry, to the right. And it's the same idea here, right? If we push on the bottom stronger than we push on the top, it'll make the disk spin counterclockwise. So how do we encode that mathematically? Well, what we're saying is that we need the change of P with respect to Y to get stronger as y decreases. So as y goes down, you could say, we need this to increase, like so. So in other words, we need the opposite of the change of p with respect to y to be positive. So we need this change to be decreasing in essence, right? So this is where I want to pause for a minute. I'm going to throw up the thinker, and I want you to look at this picture and these two paragraphs and just try to make sense of what the picture is showing. So let me do that for a minute. Okay, there we go, right? Okay, now what we're gonna do, because we have these two options that we can use to create this rotation, we're gonna add those two influences together. So we're gonna add this and we're gonna add this, and that'll give us the directed amount of curl in the k direction. Really should say k here, doesn't have to be z necessarily. In the k direction. So what I'm calling like the k curl of f is equal to the sum of these two things, partial q partial x plus negative partial p partial y, which gives you this. Or in other words, if you take the curl vector itself and you dot it with the k vector, the basis vector k, then you will get this amount. That's it. So that is why this has the structure that it does to get this type of, to get this type of rotation that you're looking for. Now you do that for every other pair of component directions and you get the complete formula for the curl, just like so. So imagine the same picture, but instead of looking down, you look from the side or you look from the back and you repeat the same argument and you will recover the same formulas that you see here. Okay. Now, I hope that makes it a little more intuitive why the curl formula looks the way it does, because that's really why it looks that way. Now, notice this. Notice that there's no curl in the k direction. if and only if these two influences cancel each other out. So if these two influences cancel each other out, in other words, they're equal, right? Then this would be equal to 0. So does that look familiar? Hopefully from the previous lecture, right? This is that formula that we were using to determine if a vector field was conservative, right? To see if it was conservative. And it was, if this ended up being 0, then you had to have a conservative vector field. Because basically what happens is nothing's getting pushed up or pushed down out of the plane. That's the basic idea. All right, so let's get back to Green's theorem now. So Green's theorem illustrates the beautiful connection between the macroscopic circulation of a vector field around a closed curve and the microscopic circulation of a vector field at every point in the region. So namely, it's this. The way you can think about it is, as long as your region is appropriate, if it's a simple region, then the circulation of F along the curve is the same as the sum of the curl inside the region. So if you want to know how much a vector field is circulating around a curve, you can add up all the individual microscopic circulation inside, as long as your region is a simple one, a simply connected region, right? That's the idea. Okay. One thing I want to point out is this, because this is why it just gets so beautiful and why these results get even more beautiful the further along we go. There's a real similarity here between Green's theorem and FTC2. This is saying that the integral over a region can be reduced to measuring something over the boundary of the region. So see, I should have changed this to partial d. That's really what it is. So Green's theorem is quite literally giving you a connection between integrating over a region and integrating over its boundary. And it's saying that if you wanted to measure this thing, then you could equivalently measure over the boundary and you'll get a similar result. I'm sorry, you'll get an equal result as long as things are set up nicely. So if you think back to the fundamental theorem of calculus part 2 from Calc 1, right? You go all the way back to Calc 1. Remember that the boundary of this interval is the 2-point set a comma b. And FTC2 just said, if you wanted to compute the integral of a function over this interval, and your function was nice enough, let's say continuous, then you could just look at the value of the function or an antiderivative of the function at the endpoints of that interval, and then take their difference. So it's that connection between inside of a region and the boundary of a region that's being generalized here. That's the idea. In fact, mathematicians often refer to the Green's theorem, or really just the divergence theorem, as the fundamental theorem of calculus. So that's really what we're talking about, the fundamental theorem of calculus, because FTC2 is a special case of the divergence theorem. That's really it. And so we're building up to that. And at the very, very end of the course, the very, very last section, we're going to get the divergence theorem. And that'll be a general result of the fundamental theorem of calculus. Okay, now let's look at the proof of Green's theorem. So because this theorem is so important, it's worth going through the proof. And because it's essentially a fundamental theorem of calculus type of theorem, it behooves us to look at the proof of it and make sense of the proof too. However, before we get to that, there's some other notation you'll see. And this is always kind of an exciting moment because when you get to look at a new mathematical notation or make sense of it, it's kind of like it's like learning what a hieroglyphic really means. So if you've ever looked in like an engineering book or a physics book and you've seen these symbols, now you know what they are. You're about to know what they are. They just mean line integral. That's it. So if you see this fancy integral symbol here with this little circle, it means you're computing a line integral, but you're computing it in the positively oriented direction. So that's what that means, positive orientation. Sometimes they'll even use a little arrow just to really emphasize that you're doing a positively oriented traverse. There you go. So that's what that means. Unlocking a hieroglyphic for you. Okay, so now we're going to give a proof of Green's theorem in the case where D is both type 1 and type 2. Basically, the regions are nice enough that we can decompose them in a certain way. These regions are called simple regions. So we're going to do the proof on these simple regions so that you can see how the proof works. Here we go. The way we're going to do that is we're going to do it piecewise. We're going to show that this is equal to this double integral, and we're going to show that this is equal to this double integral. Then we're going to combine the results using linearity to get the statement of Green's theorem. So here we go. First, we're going to express our region D as a type 1 region. So you don't need to remember the type numbers, but a type 1 region means that your y variable is passing between two curves and your x variable is passing between two numbers. And we're assuming that these two curves are continuous, or their parameterizations are continuous functions. So focusing on this equation, here's what we have. Right, here's that double integral over that region D. We can iterate this using Fubini's theorem. And I just rewrote this as, oh wait, did I? Hold on a sec. Sorry, the notation is not quite right here. This should, sorry, this should say partial y, p x y. The p should not be in the numerator, you could say. The p should be down there. So what we did was we iterated the integration process and rewrote this as the partial derivative with respect to y of the function p. And now we can apply FTC2. We can apply FTC2 and we get this. There's FTC2. So we took the antiderivative of this, which gave us just this. But of course, y is equal to g2 of x and g1 of x at the boundary. Right. Now we're going to split this into two separate integrals. So just by using linearity, we can cut it right there at the minus, and we'll have two separate integrals like so. Okay, so what we did was we just re-expressed this double integral as these two single variable integrals here. Now let's look at the line integral over C of P. Now that's the next step. Oh yeah, we're going to hold on to this for a minute here. We'll come back and refer to this in a second. So how do we compute the line integral? Well, because this is a simple region, we can decompose this curve C into four separate curves and write it as a union of the four separate curves. So here's C1 given by G1 of x. Here's C3 given by G2 of x. C2 is this line. C4 is this line. On C1, we're just going to choose x to be our parameter. It's a natural choice. So we can describe this as this vector function. So x is x, y is G1 of x goes between a and b, like so. So we can write the integral over C1 as this integral right here. That's the idea. So maybe that looks a little bit familiar. Boom, right there. Okay, now do the same thing for C3, but C3 normally goes from right to left. So that means the opposite of C3 goes from left to right, which is really what we want. So the opposite of C3 goes from left to right. We can choose x as the parameter again. And so we can describe this curve as x comma g2 of x, like so, where x again goes between a and b. So now we can write the integral of this over C3 as the opposite of the oppositely oriented curve C3, and then simplify it like so, just by plugging in our parameterization of C3. There you go. Okay, so now we've got C3 is equal to this. Now on the other two curves, actually maybe I'll stay here. On these two curves, notice that dx is equal to 0. There's no change in x, right? There's no change in x. So the integrals over those curves are going to be 0. So altogether we have this. The integral over c, the line integral over c of that function p, is equal to the sum of these four separate line integrals. But these two are going to be 0. And so what we're left with is this one and this one. Factor out a negative from both of those, and you get negative this thing right here. But this difference of integrals is exactly this double integral that we just proved a moment ago, like 2 slides ago. So there we go. We've now shown that this line integral has to be equal to this double integral over d. That's basically what we did. Now, you could repeat the process again for this line integral and this double integral here, and you'll get the same kind of result. Go through the same process, decompose that curve C into 4 curves, but you'll be able to view the region D as a, what is it, a type 2 region. Instead of it looking like this, these would be your curves, and these would be your straight lines. But again, on these straight lines, in that case, dy would be 0. So the whole argument just falls right out again, right? So you end up getting this, you end up getting this, and then when you add the two together by linearity, you get that this line integral is equal to this double integral. Boom. That's Green's theorem. Cool stuff. Cool stuff. Okay. All right. Now, let's do a couple examples. Here we go. So here, I do want you to try this one. I'll give you a little hint before we start. So evaluate this line integral where C is the triangular curve consisting of the line segments from connecting 0, 0, 1, 0, and 0, 1. So it's a triangular region that looks like this and so. So compute the line integral over this, right? But here's the thing. Think about it first. And then say something out loud to yourself about how you might start it, or to your friend, to your neighbor, to your dog, to your cat, just something out loud. Okay, now try to work it out on your own, but here's the catch. Here's the catch. Do not use older techniques. Try to use Green's theorem. Think about what Green's theorem says and implement Green's theorem here to make your life easier. And then we'll do it together in a moment. Okay, here we go. So here's the thing. We could actually use elementary methods that we've learned in the past, to compute this line integral. You just decompose it into 3 integrals over each line segment, right? And we've done that a bunch of times. However, now we can use Green's theorem, because Green's theorem says, hey, as long as your region is a simple region or a simply connected region, then if you want to compute the line integral along the boundary, you can just compute the double integral of the curl within the region. And that's exactly what we're going to do. So this integral is equal to this double integral by Green's theorem. So what we need to do is compute the partial of q with respect to x. Here's q, and here's q, and the partial of p with respect to y. Here's p. So partial q with respect to x gives us y, right? And then partial p with respect to y gives us 0. So now we're just computing the double integral of y over the region D. And the region D is simply described. You just you just scan the region from 0 to 1 minus x, and then 0 to 1, right? So it was this one. There's y equals 1 minus x. X goes from 0 to 1. Oops. There you go. And now we can do a simple double integral. FTC2 right here applied to y. And then we get this. FTC2 again applied to x. We get this. Plug in those numbers, take the difference, and you get 1/6. And that's it. Super cool stuff. So that's one of the reasons Green's theorem is so nice. All right, now how about this one? This is another one where I want you to try this. So I want you to evaluate this line integral over this curve, the circle centered at the origin with radius 3. So think about it for a minute. Okay, now say something out loud to yourself, to your friend, to your dog, to your cat. Okay, and then try to work it out on your own, and we'll do it in a moment. All right, here we go. So Green's theorem, that's what we're going to do, Green's theorem. So we can write this as a double integral over the region, because the region contained is a simply connected region. So we can use Green's theorem and everything works out nicely. So here we go. The disk is this disk. And now we need to compute the z component or the k component of the curl here. So we're going to do the derivative of this with respect to x, and then this with respect to y. That's what I'm indicating right here. This equality is Green's theorem. But differentiating this with respect to x is nice and easy. You're just going to get 7. Differentiating this with respect to y is going to be easy. You're just going to get 3. So then you end up getting 7 minus 3, which is 4. times the sum of the change in the area, but the area, I'm sorry, the region is just a circle. So the area of the circle is pi r squared. So we get 4 times pi r squared, 36 pi. Boom. Super nice. Super nice. All right. So now we get a couple of cute corollaries. Here's a cute corollary of Green's theorem. So Green's theorem really is representing another tool for us to use in our mathematical toolbox, and we can leverage it in all sorts of cool ways. Just think about how nice it was to get the fundamental theorem of calculus part 2, right? So here is one very cool application of Green's theorem. Remember that this double integral is the area of a region D, back from like, oh geez, section like 15.2, maybe 15.2. This will give you the area of the region D. Now, in light of Green's theorem, because Green's theorem gives us a connection between this double integral and the integral over the boundary, right? Let's find P and Q such that the difference in these partials is equal to 1. Let's do that. There are some possibilities that are immediate. So for example, we could set P equal to 0 and Q equal to X. Then this will certainly be equal to 1. We could also set P equal to negative Y and Q equal to 0, and then again, you will get 1. Or you could kind of do a half and half thing. You could set P equal to negative half Y and Q equal to half X, right? And those would all be solutions to this equation right here. Those would be solutions to that equation. So that means we can use Green's theorem to produce several area formulas all at once. So we get some really, really simple formulas for computing the area of a region by integrating over the boundary. Yeah, you can just integrate over the boundary and you get the area of the region. So here it is. The area of the region is given by these formulas, and these formulas are all equal. They're equal to each other. So if I want to know the area, I can just compute the line integral over the boundary of the region of the function x with respect to y. And then here I could compute it over the boundary of the region here of the function negative y with respect to x. Or I could kind of merge the two, and the area will be half of the value of this line integral where I'm doing x dy minus y dx. So we have 3 super easy uses of Green's theorem, or applications of Green's theorem to compute the area of a region. But yeah, so you try it. You try it. I want you to try to find the area enclosed by this standard ellipse. Use one of those area formulas to do it, and we'll do it together. So here we go. Think about it for a minute. Give yourself some verbal feedback. And then work on it, and we'll do it together in a moment. Right, here we go. So we can use those area formulas. We just need to be able to parameterize that ellipse. But we saw way back in chapter 12 that this is the standard parameterization of that ellipse. A cosine t, b sine t. T goes from 0 to 2 pi, and that'll take you all the way around the ellipse. Now we can use the third area formula here. You could use any of them if you want. But the third area formula happens to have a very quick and simple result. So that was this one, right? So we substitute in our parameterization and we get this. X is a cosine t, dy is b cosine t dt, right? So differentiate this with respect to t. Y is b sine t, and then dx is negative a sine t dt, right? Just differentiate this with respect to t. Then you get a really nice simplification here. You can factor out, AB from both of these terms, and then you're going to get cosine squared plus sine squared as what remains. But that's just equal to 1. So now we're integrating the unit function, which is just going to give us the length of this interval. So we get AB over 2 times 2 pi. Simplifies to pi AB, which indeed is the area of that ellipse. Hooray! It's just cool stuff. All right, so maybe even more fascinating, I find it pretty fascinating, is the fact that you can compute the area of these regions just by integrating over the boundary. And what's amazing is you can actually manifest this mathematical theory in something mechanical called a planimeter. So this is exactly what planimeters do. You can basically use these things to trace the boundary of a region on like a sheet of paper, and it will give you the area of the region enclosed, quite literally through a mechanical process. It does not need to be electronic, does not need to involve electricity. It just needs to involve some gears. Like that's about it. So yeah, exactly. These formulas say that we can measure the area of a simply connected region just by measuring the boundary in the appropriate way. And planimeters do just that. You set them up, you trace the boundary of whatever region you're interested in, and they will give you a readout that tells you the area of the region. Super cool stuff. Follow this if you want to see other pictures. There's different kinds of planimeters. There's lots of videos of them in action. And there's even this, if you want to get deeper into the math of how these things work, the AMS, the American Mathematical Society, has a complete explanation of how they work, including some historical documents for when they were first created. I think it was the 1800s? Gosh, was it the 1800s or the 1900s? I can't remember now. That's all right. You check it out. You check it out. All right. So a couple of cute corollaries there about finding the area. Um, Now let's extend the scope of Green's theorem. So we can extend this to regions that are not just simply connected. So we only proved Green's theorem for the case where D was a simple region, but you can extend it to a case where D is a finite union of simple regions. So for example, well, this picture kind of shows it. Here is a simple region that you can actually decompose into two simple regions, decompose it into a D1 and a D2, and then look at the corresponding equations given by Green's theorem. Here we go. Oh wait, just lost my train of thought. Where am I going with this? So that, C1, C3. Oh, yeah. Okay, I'm doing this. So integrate over C1 and C3. So maybe I should indicate these points right here. Those 2 points right there. So C1 is the curve that goes from here to here, and C3 is the curve that goes from there to there, just like so. So that's what we're integrating over. And this is just Green's theorem, saying if you want to know the line integral over this union, you can just compute the double integral over that region. Do the same thing for C2. So C2 goes from here to here, and then negative C3, the opposite of C3, goes from here to here. That's what that is right there. So because we need everything to be positively oriented, that's why we need to take the opposite of C3. So the line integral here is the double integral over the region D2, just like that. Now here's the fun part. If you add these two equations together, you will get the result over the entire region. But here's the thing, the integrals over C3 and negative C3 are going to cancel out. They're going to cancel out and you'll end up getting 0 there. So then that means that the total line integral is just going to be the integral over the region D. So this is helpful because it can help you decompose things and still apply Green's theorem. Maybe even more helpful is doing something like this. So what if you have a region that is not simply connected? What if you've got a region that has a hole in it? Well, you can still use Green's theorem to investigate these things. Here's how you do it. We're going to let, or how do I write it here? Oh yeah, so we're going to let C be the boundary of this region D that you see down here, right? But the boundary of this region consists of 2 curves. It consists of this outer curve, C1, and this inner curve, C2. And what we're going to do is we're going to parameterize these 2 curves so that D is always on the left, or I'm sorry, the right, the left, the left. So notice here, C1 is positively oriented. C2 is also positively oriented. It seems weird, but it's always on the left. So the region D is on the left. That's what's happening there. And now here's the trick. Here's the trick. What we're going to do is we're going to add 2 line segments that basically cut to that interior region, that interior hole, just like so. There we go. And then what we're going to do is we're going to write the integral of the region as the line integral over C1, the line integral over C2, and then that'll be it. So let me see here. How am I trying? Okay, let me connect it to it like this. Let me connect it to it like this. You can go like this. That's what we're doing. So you can compute the integral over this region, and it will be equal to the line integral over the union of those curves that I just traversed. Then you can do this region, right? And then the integral of the integral of that k component of the curl over this region will be equal to the line integral over the curves I just traversed. So this is a way of leveraging Green's theorem, even though you've got a hole here. You basically just connect to that hole. And then when you add these two results up, when you add the two results from Green's theorem together, the same thing's going to happen that we just saw in the previous example here, where the line integrals over these are going to cancel out. They're going to cancel out. That'll cancel out, that'll cancel out, and so what you'll get is you'll get the line integral over the whole thing, or the double integral over the whole region, you could say. All right, okay, so now we're going to do an interesting example. Let me pull this one up. Right, okay, so here is a vector field, a 2D vector field. So it's given by this vector function right here. And what we want to do is I want to show that the line integral over any positively oriented simple closed path that encloses the origin is going to be 2 pi. So let's think about this for a minute. If you would like to attempt it on your own, you can, but it might be a little bit difficult right off the bat. But next I want you to just say something out loud, maybe read this out loud and see if you can make sense of what it says. All right, I'm going to read it out loud again because it's always like, wait, what does this say? That's half the battle in math is when you're doing these problems, you have to read the problem like, a dozen times. So here's our vector field. We want to show that this line integral is 2 pi for every positively oriented, simple, closed path that encloses the origin. The origin, okay, well, first thing I notice is that this vector field is not defined on the origin. Okay, so there's like a hole in this region. There's a hole right there at the origin. And this is saying that if we integrate over any positively oriented simple closed path that encloses the origin, we should get 2 pi. So it doesn't matter if this is the origin right here. This is saying it doesn't matter how we integrate. We should end up getting that it's 2 pi. Interesting. Okay, interesting. So there's something going. The origin is giving us some static there. Let's take a look at the vector field itself. So this is a plot of the vector field. You can do it in Mathematica. Yeah, you can definitely see that it's getting. Yep. Yeah. So it's getting very strong the closer you get to the origin, and getting weaker the farther out you get. So if I were to do any simple closed curve, I need to show that the line integral of this is going to be 0. I'm sorry, not 0. 2 pi. 2 pi, not 0. Definitely not 0. Okay. Well, here's where we're going to use that trick. Let me maybe pick a purple pink color. Okay, think about this as our simply closed curve. We'll call it C. Now, if I needed to show that a line integral over that is 2 pi, doesn't seem immediately obvious how I would do it. However, if I put a little circle around the center there, then I can use that same technique we just saw a moment ago, where I can basically, I can like, I can do this little thing here and do this thing here. And then I can integrate like so. I think that's what I'm going to do. Let's see. Pretty sure that's what it's going to do. Okay. So since C can be any arbitrary closed path, computing it directly doesn't seem feasible. Yeah, exactly. So instead what we're going to do is we're going to put a counterclockwise oriented circle right at the origin with a radius that's small enough that it fits within the region D. All right? Small enough so it's within the region D. then the positively oriented boundary is going to be C union negative C, because remember we want it to be on the left side. We want the region to be on the left side. So then Green's theorem is going to give us this. The integral over the region is going to be the sum of these two line integrals, just like so. Okay, but now we can compute these values, just computing those partial derivatives, and this is definitely going to be 0, right? Yep, these will cancel each other out. Yep. Okay, so because this is equal to 0, that means these two things have to be equal but opposite. Yeah, okay, so if this sum is equal to 0, that means these two things are equal but opposite in sign. So that means this. Yeah, that's it right there. So the integral around C is the opposite of the integral around negative C prime, but we can switch the orientation of negative C prime and change the sign of the integral, so we get this. Yes, there it is. That makes sense. Yep. Okay, so check this out. This is a good result. Check this out. This is saying that the integral over that arbitrary path that we picked is equal to the integral over that circle. So the integral that we were interested in is equal to the integral over that circle, but that circle is very easy to parameterize. So let's do that. Yeah, put another way, these have to be equal to each other. Yeah, these have to be equal to each other. So that, the integrals here are going to be equivalent. They're going to be equal. We can easily parameterize that circle. We'll just use the natural parameterization a cosine t, a sine t. And now we can just plug in this parameterization and compute. Here we go. So the integral around that arbitrary path, c, is equal to the integral around that circular path, c prime. Now we can substitute in our parameterization, go from 0 to 2 pi. This is our force field with our parameterization plugged in. Okay, now it looks very messy at first, but when you actually compute the dot product, dot this, multiply those, add the results, you should get a bunch of cancellations, I think. A times a squared, a times a is a squared, a squareds cancel. Then you're going to have cosine t sine t, which is 1 in the bottom. Here you're going to have, again, sine squared, cosine squared, which is 1. So all of this simplifies to 1. And behold, we get 2 pi. There we go. We get 2 pi. Yep. So that's a tricky one, huh? But it shows you how nice Green's theorem can be. Green's theorem can give you a lot of leverage for these types of things. We basically had a totally open-ended question where it's like, hey, show that the integral around any one of these paths has to be 2 pi. And that really just came from the fact that the line integral around that path is equal to the line integral around any circle. So that was kind of the first bit of the whole argument, right? That those two line integrals are going to be the same. Then we just computed the line integral over the simpler path and got 2 pi. Yep, that's the idea. Incidentally, this is also related to the residue theorem. So if you did follow that link to Cauchy's integral formula and the residue theorem, this is actually an artifact of that more general theory right there. The fact that you're getting 2 pi in particular. Okay, so we're almost done here. I know this is already a lot, so thank you for bearing with us so far. We're going to finish up by doing a very nice quick proof of that theorem from the last section that we didn't prove. So here we go. Remember there was that theorem that we came up with that basically allowed us to determine if a vector field was conservative, and it said, hey, as long as you are, if your vector field is defined on a simply connected open region, and your component functions have continuous first order partials, and this difference is 0, then your vector field must be conservative. Well, now we're going to prove it very easily using Green's theorem. So all that buildup to get this very, very quick result. It's like 1 or 2 paragraphs, that's it. So let C be any arbitrary closed simple path in D. Let R be the region that C encloses. Then Green's theorem gives us this. The line integral of that vector field on C, we can rewrite it in terms of its components. Green's theorem gives us this connection, that this line integral is equal to this double integral. But because we are assuming that this is 0, We're now doing a double integral of the 0 function over some region. So the answer is 0. This is going to be 0. Now, this is true for any arbitrary simple closed path, right? But a curve that is not simple crosses itself at one or more points, right? Like so. However, if it's crossing itself, then what we can do is we can actually decompose it into two simple regions, or two simply connected regions, right? Or simple closed curves. The line integral of f around these simple curves is going to be 0 by this calculation. So if we add up all those results, that means the total line integral is going to be 0. Thus, this line integral is independent of path, right? Because remember, path independence was equivalent to the line integral being equal to 0 for any closed path, simple closed path. So because this is independent, f must be a conservative vector field. Boom, there it is. All right, whew, okay. So on that note, it's time to play. Thank you again. I know this is a lot of stuff. These two sections are just very deep. There's so much stuff to learn. There's so much stuff to process. Give yourself some time to process these things. We will work on activities related to this in class. Other than that, thank you again for listening. Thank you again for watching, and I will see you next time.